Did it record it? Okay.
Okay, so let's have this section of the class. We will finish about 1:15, then go to the lab, and Casey will do a demonstration of texture analyzer. And it may not be calibrated, then he will just do a demo. Okay, I'll show you something here. So this part, we'll talk about minerals and the texture analyzer. Because minerals, you learn in your other nutrition classes a lot. So we're just going over it briefly. Okay, so first thing when we talk about minerals, so what is minerals? So I will say is organic or inorganic form, or we say formation of salt. Of course, it is important in food products or for the human function. And I gave you some of the examples we'll talk about. Let's say a phosphorus is combined with phosphoprotein, and the metals is with an enzyme. Those are the examples. Now, they do a little bit of research. They find that the natural elements, about 90, 25 essential for life, 60 is in the food products. And they, based on the dose, they will say it's a major and minor, or they say trace. Now what's the difference between that? This is more than 50 parts per million per day for human consumption, and this is less than 50 parts per million per day. And we know that the major one, let's say sodium, calcium, potassium, calcium, phosphates, and sulfide, and bicarbonate, what else? Magnesium, all these, okay? Trace most of the others. Here, more important for the survive, ferric, iron, and copper, and copper. Those two are most important. So this is just give you an overview of the minerals. What is minerals? Naturally occurring in organic salts. This is give the example, the main elements in the human body. So basically, the major components is calcium, 10 to 20 grams per kilogram, followed by phosphorus, potassium, sodium, chlorine, and the magnesium, chloride and the magnesium. Now, be careful about this calcium. We will mention later on. The calcium synthesized by vitamin D, and we have to maintain a certain level of the calcium. And if the calcium is deficiency, is not enough level in the blood stream, and your blood level calcium is not enough, then it will be taken out from your bone. So you may have some bone dysfunction or deformation problem if the calcium is not enough in blood concentration. So maintain the calcium is very important. This tells you the mineral content of some food products. So you can see the milk, egg yolk, and this beef. These you can see a high level of sodium, higher level, slightly higher level of potassium, and you start to find the calcium level is start to decrease. Okay, just give you an idea. Then I want to mention one thing. Here is a calf liver. In the traditional Asian style cooking, we eat swine and pig liver. It's a byproduct here in the Western style diets, but in the China or Vietnam or Korea, Japan, or these Asian countries, pork liver is a food. You can see it's a very prolific level of those minerals. Sodium is okay, potassium is higher, and the phosphate level is higher. That's a good resource. But the only thing bad for the liver is because it is a major metabolic organ, so the lipopolysaccharides, the LDL is actually a little bit higher, and the cholesterol level is also higher. So people will be encouraged to eat some of the liver, but not eat too much because cholesterol is high. Then you go here, you see flour, kernel, they are okay. But when you move down here, you will see spinach. It's a big resource for all the minerals. And there is a debate about whether you should cook heated or you eat raw spinach, because the potassium level is very high. So some people will say if you heat it too much, the potassium level will decrease. But some people say you should eat raw because you're going to take in potassium, but they also have a concern about some toxication of the potassium. So you can see spinach, very high amount of all these minerals. Okay, so this gives you an idea mineral content in some of the food products. Now, this moves here, we're going to talk about a little bit of chemistry. One of the minerals will be existing, the formation of the minerals existing in a food product. So, if we want to keep it right here, what are the formation? This is question number 1. This is question number 2. Number 3 will be the formation. So first of all, it can be an ionic formation. This is everybody knows, sodium chloride. It is an ionic formation. Second, that could be called acid or base. Here the base, which means alkaline. Acid and base salt. For example, sodium phosphate, calcium phosphate. Then it could be called ligands. Let's say magnesium oxalate. The last one, if multiple ligands combine together, become chelates. Let's say calcium EDTA. So basically, this is the 4 different types of the formation of the mineral in a food products. And then we'll briefly introduce each of them. Okay? The first one, we want to introduce your concept in a chemistry, in the chemistry level area. We talk about the concept of acid and base. Now this is typically for the phosphoric and hydrochloric acids salt. There is 2 different types of the serum. Number 1 is called Bronsted. Bronsted, which means if you have a proton donor, this is called acid. If you have a proton acceptor, this is called base, which is alkaline. And they give you an example, is phosphoric or phosphate. You can see the phosphate. If you dissolve the phosphate in the solution, that could be mono, di, and triphosphate. And with a wide range of pKa value from 2.22 very acid to 12.40 very alkaline. Therefore, therefore, the phosphate is a good solution for buffering. So a good example here is a phosphate solution. Because of wide range of the pKa values, it is a good buffering solution. Good buffer. So you know that we're not manufacturing foods in the lab, but you know when we were cultivation of bacteria, we sometimes using 0.5% saline, 0.9% saline solution, or 0.1% PBS, or buffered peptone water. Sometimes we also use PBS, phosphate buffered solution, at pH 4.7.2. This is used to make sure the pH value of a bacterial solution is being buffered. So that's a good example for the phosphate. The second is called Lewisiria. Lewisiria is different. So here we talk about is proton donor and acceptor. This is we talk about is electron. So acid is electron acceptor, and the base is electron donor. And I can give you an example. So how we understand this? This is A, let's say, add B. Or sometimes we say this, then become AB. If you want to draw, you can say they share this. A and B, they share this. This formula right here, this A, they must process electron. And this B, they must be donate electron. Then they can share it. And the number here, we call it coordination number. This coordination number usually is between 1 to 12. 6 is the most widely existing in the food products. And here give you example. A ferric iron, if in an acid environment, is coordinated with 6 water molecules. And I give you another 2 example. Not really 6, but you should know another good example of the acid base. What are the 2 examples? Hemoglobin. What is the hemoglobin looks like? It's right in the middle. And this is actually goes here, and this is going to be this going to be right here will be this is the hemoglobin example. Second example, chlorophyll. Chlorophyll. In the middle is a magnesium. Then you also have these. But these 4 will be this has to be the different position. Magnesium sulfur and hemoglobin, those are the two examples, which is the acid base combined. Okay? Therefore, we gave out another example, which is move to the ligands. Now, what is ligands? This means the electron donor species. All of these three examples here is monodentate, bidentate, and the bidentate right here. Oxalate is one of the good examples. They must contain an oxygen donating atom. It could be oxygen, could be nitrogen or sulfide, but they have to be. This formula here, which tells you how they categorize ligands, based on how many numbers can be attached to one metal ingredient. So they use M plus Ln, become MLN, and come out this formula, the K, which means constant formation, constant value. So this is well determined by every ligand, how many available ligand number could be combined with one single metal. And a good example right here will be the oxalate organizer. And then the question is, what gonna be this reaction happen? How easily this reaction will be happen? Then same with other biochemistry reaction, determined by Gibbs free energy equation. Delta G is, we call it a free energy. Delta H, we call it enthalpy, and delta S is entropy. Now what I want to mention here is the T. That T is Kelvin temperature. It's international units of temperature. It is not degree Celsius, not degree Fahrenheit. It's Kelvin. And what that means is 0 degrees Celsius equals 273 K. Okay, so at this moment they are using the T as absolute temperature. That is Kelvin. Now, how do you know this reaction will be happening spontaneously? Once the delta G is negative, then this reaction will happen spontaneously. If delta G is positive, it's not going to happen spontaneously. You need to use enzyme to let it be happen. Okay, so this is called a ligands. Good example, sodium oxalate. However, you may not be familiar with this because this not happened in the, like just a simple or single formation for the mineral in a food products. Not often happens. Most of the time, they'll happen as a chelate. So, this is a chelate. So what is we call it a chelate? Chelate is a multiple ligand combined together with a metal. That's called a chelate. It's like a bird have the feet, which is grabs these lines, and electronic lines in the above the tree. So then they will have some critical factors to determine how stable the metal ions with the ligand. And it listed here is 7 factors. But basically, we understanding is that if there is more members involved, will be more stable than single members. So, for example, this ferric ion in an acidic condition with 6 molecules of water, it will be less stable compared to here, the cupric, cupric, which is combined with water. Okay, here with water, with ammonia, with amino base, and with hydroxy base. So more members will be more stable. Second, it depends how many rings. In a chelate, the greater number of the rings will be greater stability. So look at the EDTA. You can see here there are 5 rings here. So it's more stable compared to the single ring. That's why the calcium EDTA is a very popular chelates using food products. Because of so many rings there, it makes it very stable, can prevent oxidizing products. That's we can say it's prevent pre-oxidant. Okay, so that's a good example. Also, the research find that stronger Lewis base will form stronger chelates, which means high pH value, and the low pH value will end up with a weak chelate. Now, charged ligands will be more stable than uncharged ligands. And then you go here, you will see different formation of the oxygen nitrogen sulfide at the donor will have a different level of the stability. And the enhanced reticence will increase stability, and the large bulky ligands will be less stable than the smaller one. Okay, so just to give you an idea, if ligands have a multiple ligands formed, combined, and then have a multiple bonds combined to a metal ion, that become a chelate. And the EDTA calcium is the most popular one used in the food products because it has a multiple rings, has a multiple memberships and member groups, and also that pH is a little bit higher. That pH about like 10, so that's why it's more stable. This slide which it talks about, in our food products, when we eat something, the absorption of the mineral usually will be impacted by the other food components. So for example, the mineral absorption will be decreased by the fiber. Why? The reason is very simple, because fiber will be reacted with iron, zinc, and even calcium. They'll cause precipitation. So let them not easily to be absorbed in the body. Now why? Because there is a phytate present in the fiber. And the phytate, you can understanding this is a plant acid, which is acid products in a plant resource. So they're very easily to be attracted, all these ions, the zinc, all these things. Kind of like in a plant products, you have acid like a broad statol, and also have a Lewis base acid there. So they can easily attract these iron and zinc. Now, in the opposite direction, if we are preparing a meat, then you will see a meat products is easily to be attracted ions. And the iron in a meat product will be bioavailability increased to be used by the human being. Because the amino acids, polypeptides can chelate non-heme iron. And for nitride-cured meat, because we have a citric acid, ascorbic acid, and aerosobic acids, so the metal products in a meat, in a nitride-cured meat, is easily to be used and digested compared to their in a single format. So just give you an example, fiber and the meat, they play a different role for these mineral compounds in the body. Now, here we're going to go over something really simple, because you learned in your other nutrition classes. Just go over these each ingredients. Sodium, for example. Human body has 1.4 kilograms sodium. To maintain osmotic balance, which means you're not going to lose too much water, you're not going to lose attracted too much water. Maintain the balance. FDA require you no more than, or recommend you no more than 2 grams salt per day. Now, there is a study did the survey. Average Americans eat every day 3.4 grams salt. That is not good, because high salt will cause high blood pressure. That's why we have to control the sodium value in our diets. Now the sodium, at the beginning when we find it, it's a good food preservation because it will kill bacteria or inhibit bacteria grow. Later on we find it provides flavor and also improve the texture. So this is about sodium. Second is potassium. Potassium is about 2 grams per kilogram in the human body, and it's a most predominant in the intracellular fluid, and they will be most of the time to regulate osmotic pressure. If there is not enough sodium, it will play a role as an alternative for the sodium to make sure the osmotic balance. However, in our real life, often the time we are consumed too much sodium, we eat too little potassium. And here you will see this is the daily allowance, depends on the age. Now, like us, we are more than 13 years old, daily allowance 4.7 grams. That's 4,700 milligrams. Lactating women need a little bit higher than that. Magnesium. Magnesium is about 250 milligrams per kilogram in the human body. Daily requirements 300 to 400 milligrams per day. Daily take average in the United States a little bit higher than that, somewhere 300 to 500. Naturally existing in many foods, it's activator for many enzymes. The deficiency could be serious, but it didn't mention how serious it is. We believe probably not going to be too much case of the deficiency because it's natural abundance in many foods. Calcium, we mentioned about the calcium. Abundance in the body, 1,500 grams in adults, muscle function, most of them in skeletal tissue. Now I mentioned earlier, you must meet the requirements, otherwise it will be reabsorbed from the bone. So what we have to do, taking the vitamin D and do the sunshine. So if you're taking a nutrition class, and Natty will tell you, in West Virginia, from October to April, the second year April, you're recommended to take the vitamin D supplements, maybe 1 or 2 every day. How about from April to October, which is later spring to the summertime? You're going to have a sunshine every day, about like 30 minutes. So you will get some vitamin D from the sunshine. So it transform become